Okay, so this is the last part of this chapter about vector spaces. So we are going to see the link between vector spaces and linear systems. Okay, let's start with the definition about row space. Okay, so the row space, of a matrix is the span of the set of its row. Okay, of its rows. So the row rank is going to be the dimension, so you can guess. The row rank is the dimension of that row space. The row rank is the dimension of this space, the row space. Okay, so that means it is the number of linearly independent rows. Okay, so let's have a look at this lemma. If two matrices, okay, so if two matrices A and B are related by a row operation, A. So if we swap, okay, if we do some swapping, okay, row I, we swap row I with the row J to get the matrix B, or if we rescale row I, so K times row I to get matrix B, or if we take linear combination, okay, so if we do K times row I plus row J, okay, so if we do any of these row operations for I different of J and K being non-zero, of course, okay, then their row spaces are equal. Hence, row equivalent matrices have the same row space, and therefore the same row rank. Okay, so the question is, what is the link between the vector spaces and the linear system? Okay, if you remember, when we studied the linear systems, we said that sometimes we can write a linear system of equations as an augmented matrix. Okay, so, and we have also seen that if we have an original matrix and we perform Gaussian operations and get an echelon form matrix, then the solution set of those two matrices are the same. Here in this lemma, we see that if we have those two matrices, original augmented matrix, perform Gaussian operations, and we get the echelon form, then we are not changing their row ranks or their row spaces. So we are not changing their row spaces, therefore their row ranks. So basically what it means is the information in the matrix, in the original matrix, is preserved. Okay, we are not changing the space, the row space, or the row rank. Okay, so let's continue with another lemma, number 3. Lemma okay. The non-zero rows of an echelon form matrix. Okay, those rows make up a linearly independent set. Okay, so I am going to stop this first part, or this first section of the 6th part here. We will stop here. This we have talked about a row space and a row rank. And what I'm going to do is in the next video, I'm going to do a tutorial, one example about how to find a basis and the rank of a matrix. So if we are given a matrix, as the lemma says, we are given a matrix, we perform some Gaussian operations and we get the echelon form. Okay, we get the echelon form. Then this lemma says the non-zero rows. Let's say we have performed and we have only one row here that is 0. So the non-zero rows form linearly independent sets. Therefore, the element of the non-zero rows are the element of a basis. So these non-zero rows form a basis for that row space. Okay, so that's how we are going, in the next video, we are going to find a basis and therefore a rank. That means the dimension of the row space. Is that okay? Okay, see you. Thanks.